Today we're jumping into a landmark paper from 2013 that taught computers to understand language in a way that honestly feels like magic. This single paper is basically the foundation for so much of the AI we use every single day. So how'd they pull it off? Let's get into it. Okay, so it all kicks off with this question that just sounds impossible, right? I mean, we think of computers as number crunchers and words as, words. So how could a machine possibly do arithmetic with concepts? Well, that is the big mystery we're going to unpack right now. So check this out. The researchers behind the paper put this exact equation on the table. Take the vector for Madrid, subtract the vector for Spain, and then add the vector for France. What do you think you get? What concept is to France what Madrid is to Spain? The answer? Well, it's pretty mind-blowing. The computer answers Paris. And what's crazy is it gets it right with this incredible accuracy. Now, this isn't some pre-programmed, hard-coded fact. The machine learned this relationship just by reading tons and tons of text, and that is the magic trick we're about to break down. All right, so how on earth is this kind of word math even possible? It's not actually magic, of course. It's a brilliant idea about how to represent what words mean. Let's pull back the curtain. So, the whole secret, the big idea, is to stop thinking about words as text and start thinking of them as points in space. Imagine a giant multidimensional map for every single word, kind of like a GPS for meaning. Okay, so the fancy term for this is distributed representation. All that means is that every word gets turned into a vector. You can just think of a vector as a big long list of numbers, kind of like a recipe. This recipe of meaning tells the computer exactly where to place the word on that huge map. Now, these aren't dimensions we can easily name, like size or color, but abstract dimensions of meaning that the model learns all on its own. And what's so cool is that once you have this map, these amazing patterns just appear. As you'd expect, similar words like dog and puppy end up really close together. But it's more than that. Consistent relationships, like between a country and its capital, they form parallel lines. So the trip you take from the Spain point to the Madrid point is the exact same direction and distance as the trip from France to Paris. Okay, but that just leads to the next big question, right? How does the computer actually build this incredible map in the first place? Well, the model from the paper, it's called the Skip-Gram model, and its goal is actually super simple. It all boils down to this really simple old saying, you shall know a word by the company it keeps. So what makes a river a river? Well, it's because it's always hanging out with words like water, flow, bank, and boat. Its neighbors define its meaning. Okay, so here's how it learns. It's this simple loop. First, the model grabs a word, let's say river, and it tries to guess the words around it. At the very beginning, it's just guessing. It's terrible at it. But every single time it messes up, it makes a tiny little adjustment, a nudge, to the river vector, trying to get just a little bit better for next time. Now do that billions, and I mean billions of times, and suddenly that amazing map of meaning starts to take shape. All right, but doing something billions of times, that sounds really slow and computationally expensive, right? Well, the authors of this paper came up with some really clever shortcuts to make the whole thing not just possible, but actually super efficient. I mean, think about words like the, or in. They're everywhere, but they don't tell you much about the specific meaning of a sentence. You can imagine the model would waste a ton of energy just learning that the word the shows up next to, well, pretty much everything. So the first clever trick was something called subsampling, which basically tells the model to strategically ignore a bunch of these super common words. The other big innovation is all about how it trains. The old way, hierarchical softmax, was smart but complicated. This paper introduces a simpler, way faster method called negative sampling. So instead of giving the model this super hard pop quiz, like guess the right word out of thousands, negative sampling gives it a much easier multiple choice question. It's like, hey, here's the real neighbor, and here are a few random fake ones. Just tell me which one is real. That's a way easier problem to solve, it's way faster, and it turns out it works like a charm. And you don't have to take my word for it. The proof is right here in the data. This chart comes straight from the paper, and it shows the accuracy on that word analogy task we talked about at the beginning. You can see clear as day that negative sampling, that's the NEG bars, it just crushes the older method, especially when you give it more fake noise words to learn from, like with 15 negative samples. Okay, so single words? Check. The model gets it. But what about phrases? Where the meaning is way more than just the sum of its parts.
The authors use this perfect example. Yeah, if you just add the vector for air to the vector for Canada, you're not going to land on the airline Air Canada. It just doesn't work that way. So the model needed a way to understand these multi-word ideas as a single thing.
And the solution? You guessed it. Simple but really powerful. Before training even starts, they have a process that looks for pairs of words that show up together way more often than you'd expect. It then basically glues those words together, making a brand new token, like New York_Times, and then it learns a unique vector for that new phrase, just like it was any other word.
And no surprise, the results are seriously impressive. Look at this. The model figures out that Montreal Canadiens is to Montreal what the Toronto Maple Leafs is to Toronto. It can even connect executives to their companies. This just shows it's not memorizing stuff. It's learning these really complex, real-world relationships.
So, all of this leads to a much bigger question. When a computer can do this kind of math with concepts, what does that really mean? Is it beginning to understand?
And it's not just analogies. The model's power goes even deeper. It turns out you can literally just add vectors together and get results that make total sense. Russia plus river, you land right next to the vector for the Volga River. German plus airlines, boom, Lufthansa. This shows there's this really deep logical structure to the map of meaning the model built.
Look, at the end of the day, what this paper showed was nothing short of revolutionary. You could capture these really complex, nuanced relationships between words using just simple math. And this wasn't just some cool party trick. This discovery was a fundamental building block for all the huge language models we use every single day now, in our search engines, our translation apps, all of it.
Which leaves us with one last, kind of mind-bending thought. This paper proved that to a computer, meaning can be a location, a direction, a point on a map. But if that's true for a machine, what does that imply about the nature of meaning itself? What does it say about how our brains understand the world?